All right, so we're going to try to do an application, a simple application using spherical coordinates and Cartesian coordinates. And a simple problem will be, albeit a little bit artificial, will be to calculate the distance between two cities. And for this exercise, we're going to pick Paris, let's say, and Los Angeles. So I already drawn a picture of the Earth. So this is the Earth over here. And I put my Cartesian coordinates, y, x, and z. So z here, I have it pointing along the axis of rotation of the Earth, and the x-axis comes out from the center and it goes through the prime meridian, the green one here that goes through Greenwich and comes out here. And then at 90 degrees to that, I have the y-axis, and at 90 degrees to both of those, I have the z-axis, which is along the spin axis of the Earth, like I said. So this is the center of the Earth over here, O, and this vector here, v1, right, goes from the center of the Earth to a point on the surface, which is Paris. Okay, and then we also have another vector that goes from the center of the Earth up to Los Angeles, over here, LA. And so what we would like to do is calculate the distance between those two cities. Now, there's different ways of thinking of the distance. One way is just to take the straight line path between the two cities, and in three-dimensional space, that shortest distance, that straight line, would go through the Earth. So we're going to calculate that distance first, but then we're also going to calculate the way if you're actually going to travel between Paris and LA without digging a tunnel, doing it along the surface of the Earth. And the shortest distance between Paris and Los Angeles is going to be along the arc of a great circle that goes around the Earth. So the equator is a great circle, right? Whereas the other parallels, they're not great circles in that they don't connect points using this shortest distance, whereas great circles do. So all the meridians, they are all great circles that are go through the pole. The equator is a great circle, but this time we'll have to find a great circle connecting Paris and Los Angeles, so one that goes something like this. So we're going to calculate these and we'll calculate the distances. All right, so here we go. So the first thing is we'll have to find out the latitude and longitude of both cities, and we're going to denote them using r, phi1 being phi2, I want to use 2 for Paris, and lambda 2. So radius, which is just the radius of the Earth, r is equal to 6,371 kilometers. So that's the radius of the Earth. And then phi2 is the latitude of Paris, it's around 48 degrees, and lambda 2 is the longitude of Paris, is around 2 degrees east. And then LA, it's going to have coordinates also. It will be the same r, right? It's on the surface of the Earth, also 6,371 kilometers. But now the latitude and the longitude will be different. And one thing we'll have to be careful is that the longitude for Los Angeles is going to be westward, west of the prime meridian. So this one we'll have to give it a negative angle measured radians because we're moving from the prime meridian in a clockwise direction as opposed to a counterclockwise, which is a positive direction for the angles. All right, so the first thing we'll do is we'll convert the spherical coordinates to Cartesian coordinates. And so for Paris, that's easy, x2 is equal to a, or r here, let's call it a, because that's that particular coordinate value, a, which is 6,371 kilometers. A times the cosine of phi2 times the cosine of lambda 2. And then y2 is equal to a cosine of phi2 sine of lambda 2. And finally, z2 is equal to a sine of phi2. So that's Paris. And now Los Angeles, x1 is equal to a cosine phi1 cosine lambda 1. y1 is a cosine phi1 sine lambda 1. And z1 is equal to a sine phi1. All right, so now we have those distances. Now, if you want to find the straight line distance between Paris and Los Angeles, what we need to do is calculate the length of this vector, the one connecting Paris to Los Angeles. And we can calculate that one by first, if we start in Paris, right? Start in Paris, and we travel to the center of the Earth, right? So that's minus This is minus this vector here, which I call v2. And then we add back the vector going from the center of the Earth to Los Angeles. That's plus v1. v1. 1. All right, so that distance, if I add this to that, I end up with this vector. And this vector here, which is v1 minus v2, is the vector connecting Paris to Los Angeles. And now I will want to calculate the distance of that vector. So that vector, v1 minus v2, it's easy. We can just calculate by taking the difference of all the coordinates. So that's going to be x1 minus x2, y1 minus y2, and z1 minus z2. And now the distance, which is going to be the length of that vector, so the straight line distance d, is going to be equal to the square root of x1 minus x2 squared plus y1 minus y2 squared, squared, plus z1 minus z2 squared. There's my brush. So that would be the distance along the straight line connecting the two cities. So a convenient way to write that, this sum of the squares of the components, is this way. Square root of v1 minus v2 dotted with v1 minus v2. So the dot product, remember, is going to be the first component of the first vector times the first component of the second vector. So that'll be x1 minus x2 times, and this is the same vector, x1 minus x2, so it'll be the square, and then y1 minus y2 plus, or times y1 minus y2 will give you the second squared, and so on. So that is a convenient way to get at the distance using the dot product. All right, so now we would also like to compute the distance going along the great arc, right? The arc of the great circle. And for that, the easiest way to do it is to calculate this angle here between v1 and v2. So this angle, I'm going to call that theta. And if I know theta, then I could calculate the length of the arc, because theta times the radius of the Earth gives me the length of the arc, right? Because theta gives me the fraction of a full circle. So if a great circle, its circumference will be 2 pi times a, which is the radius of the Earth. So 2 pi is the angle measure of going around the whole Earth. And this time I'm not doing the full circle, I'm just doing part of it. So the first thing is calculate theta. So how do we calculate theta? So that's the question. And for that, we're going to use the dot product again. And the definition of, you can think of it as the definition of the cosine of an angle is defined through the dot product. So if I do v1, the vector, this one, dotted with v2, then that is equal, that's true in general, is equal to the length of vector v1 times the length of vector v2 times the cosine of the angle separating them. And so I could turn this around now and solve for theta 2, right? So plugging in what the lengths are, this is, the length of v1 is just a, the length of v2 is also a, and cosine of theta, I don't know why I put 2, just theta. And then I can now solve for theta. So theta is going to be the arc cosine of v1 dotted with v2 divided by a squared. And this will be the angle. And now the distance along the great arc, d, will be just theta times a, the radius of the Earth. All right, so that's how we will do it. We'll solve it on the computer to skip all the arithmetic of plugging in real numbers. But that is how we're going to do it. As an exercise, you should try to calculate the difference in the distances between these two. Which one is longer? Of course, the arc will be longer, but by how much? And then, as another exercise, try to find out how deep into the Earth the tunnel would have to be. What would be the deepest point of the tunnel connecting Paris and Los Angeles if we were to dig such a tunnel? And maybe you could see if it would be deep enough to go below the deepest point of the ocean, the Atlantic Ocean. All right, that's it for now. So lat ln of Paris, and that is 48.8566 north. And so this is in degrees. We'll have to convert that to radians, which is not too hard. just multiply by pi and divide by 180 degrees. And then the longitude is 2.3522 east, which is in the positive direction, right? So when we do Los Angeles, well, let's do Los Angeles now, but we'll see that Los Angeles has a longitude which is to the west. So lat lon of LA, Los Angeles, right? So it has 118.2437 degrees west. So that will be a negative angle measure, right? Because it'll be going westward, whereas going in the counterclockwise towards Paris from the prime meridian is positive. All right, so let's calculate these distances. So I'm going to do this in Julia, and my text editor is Atom, but you can use a different text editor if you want to try this in a different zone. All right, welcome back. Now we're going to type in a Julia function to convert spherical to Cartesian coordinates. So the word function is a keyword in Julia, which means I'm defining a function. The inputs to this function is r, phi, and lambda, and the name of the function is s to c. To type in the Greek letters, the way I do it is I do a backslash followed by the name of the Greek letter. So for example, phi, and I hit tab and it converts it into the Greek letter. Another keyword is return. So inside a function, the return tells the compiler what are going to be the outputs for this function. In this case, x, y, and z, there's 3 outputs. The radius of the Earth, A, I enter it to be 6,371 kilometers. So that's the only place a length comes in to these calculations, so everything will be in kilometers from now on. First, I enter the coordinates for Los Angeles. Phi1 is the latitude, that's 34 degrees north, so that's a positive angle measure. And I convert into radians by multiplying by pi and dividing by 180. Then lambda 1 is the longitude. LA is to the west of the prime meridian, so then I get a negative angle measure, so minus 118, again multiplied by pi divided by 180, and I turn it into radians. R1, the radius, connecting the center to Los Angeles, is just the radius of the Earth. Same thing for Paris. 48 degrees north, a little bit further north than Los Angeles, and convert it to radians. Then lambda 2, that's about 2 degrees east, so it's to the east of the prime meridian, so it gets a positive angle measure. That's the longitude. And then the radius is A again. All right, now I'm going to convert these spherical coordinates into Cartesian coordinates using the function I created at the top, s to c, putting in r1, phi1, and lambda 1 for Los Angeles, and same thing for Paris, using the r2, phi2, and lambda 2. Next, I'm going to create vectors, so v1, the vector from the origin to Los Angeles. Then v2, the vector connecting the origin to Paris. And now I'm going to enter the difference between v1 and v2, which is the vector connecting Paris to Los Angeles. Not Los Angeles to Paris, as I wrote in the comments. That doesn't matter anyways, because when you take the distance, you get the same answer. The distance from Paris to LA is the same as the distance from LA to Paris. So I'll get the right answer anyways, even though my comment is backwards. So this is the straight line distance, and the way I do the dot product is using the matrix multiplication with the prime, which means a transpose. So dv is a column vector, and dv prime is a row vector, so dv prime star dv is the same thing as the dot product. Then I use the same trick inside the Arcos formula to get theta, and then I get the distance along the great circle by multiplying the angle by the radius of the Earth. So now to run all this code, in my Juno environment, inside the Atom editor, I just do shift return, and that will compile and evaluate each line. The little check mark means everything evaluated okay. And then to see the answers, I'm just going to type in d1, d2, and the difference between d1 and d2. Answers are in kilometers.